welcome to Saturday's edition of Cracking the Cryptic. And we've released a special video actually earlier today. It's called Our Astonishing Viewers, and it's a testament to you guys. Basically, we've just tipped over 150,000 subscribers on the channel, which is more than Mark and I could have believed in our wildest dreams. And over the time we've been doing the channel, which is nearly 3 years now, we've received some astonishing emails and comments, many of which have made us laugh. And yeah, well, we put them together. Kurt Hugo Schneider's provided us with some amazing music, and I definitely recommend it to you. I will tell you that Mark did most of the work on the video, and I have to watch it in private because I get a bit emotional. Anyway, what else is going on in Puzzle World? Well, we've got on Patreon at the moment, our Sudoku puzzle hunt is still going strong. There's hundreds, literally, of comments from you guys talking about the puzzles and how to solve them. Do check it out. Just click on the link under the video, and that will take you to somewhere where you can download it. It's free. It's not behind the paywall on Patreon. Also, for those of you who do sponsor us on Patreon, I'm going to be putting up a puzzle later by Mike Haldeman. It's an anti-night Sudoku. So there's a little bonus there for you guys, which I'm sure you'll enjoy. If you've been following the channel for a while, you'll know that Mike does very nice puzzles. So yeah, hopefully that'll be good. What else? Oh, Mark, yeah, during our self-isolation lockdown, we are continuing our schedule of 2 videos a day. I think Mark is going to be looking at a puzzle by Bastien Vialgem later on. Now, Bastien, for those of you who don't know, is from France. He's one of the world's very best Sudoku solvers, probably top 5 in the world, and he is also an unbelievable compiler. So his puzzles are always good, so that'll be worth checking out. And what have I got for you? Well, I have a puzzle by none other than Ard van der Wetering. Now, Ard sent us a puzzle just over a month ago, which was based on a magic square, and this one has 2 magic squares in it, believe it or not. And that video that I recorded on his puzzle now has over 3 million views. So yeah, that is a testament to the quality of the puzzles constructed by Ard. They are absolutely awesome, and that is what we're going to try and solve. Now, I should tell you the rules of this one. They are very unusual. You can see we've got 2 marked diagonals. Now, these are not the numbers 1 to 9. Normally, marked diagonals are illustrating the numbers 1 to 9. In fact, in this puzzle, all we're saying is that these have to be odd digits. So they've got to be odd digits on these main diagonals. Now, the 2 rhombuses in the grid are actually magic squares. So if you sort of look at them like that, they become magic squares. And so in a magic square, every number in the magic square needs to be a distinct number from 1 to 9, and every row, every column, and every diagonal in the magic square needs to add up to the same number. And apart from that, this is normal Sudoku. You can see there are only 4 given digits here. Now, if you haven't tried an Ard van der Wetering puzzle before, I can tell you that Ard strives, I think, for minimalism. So it is very unlikely that there is any superfluous information in this puzzle, and sort of more than one way of solving it. Certainly at the beginning, we will have to spot something, no doubt clever, that will allow us to make some progress. I mean, these are a joy. So do have a go. You click on the link under the video to play the puzzle. Now, let me start. In fact, I should say, let's get cracking. And I would just want to revisit magic square logic, which we did in the 3 million view video. So let's imagine this this box down here is a magic square, just to keep things from being tilted on their side. So if we know that every row, every column, and every diagonal in this box has to add to the same number, we can do a bit of arithmetic to help us out. Because we know that this box in a Sudoku, if it contains distinct digits, it must add up to 45, because it will contain the numbers from 1 to 9. Now, we also know, if there are 3 rows in this box, that each row must therefore add up to 15, i.e. 45 divided by 3. So we now know the sort of magic sum for the magic square. Everything in it has to sum up to 15. Now there are some things that we can establish straight away then. And in this regard, it's not maybe a bad idea to look at this magic square up here, because the grey lines are a clue to how we can make a bit of progress immediately with the digits. Because if you look carefully, you can see that whatever digit we place sort of at the centre of the edges of the magic square, that has to be part of two different sums that make 15. So if we look at this one very specifically, those three squares have to sum to 15, and these three squares have to sum to 15. So that this, whatever we put here, can only be part of two sums. Whereas if we look at the corner squares, look, the corner squares in the magic square can be made, 15 can be made in three ways. And finally we get to the centre square, and the centre square can be made in four ways. It can be made once from this diagonal, once from that diagonal, once from this row, and once from the column. So the central square in a 1 to 9 magic square is the only digit that can be part of four different sort of separate sums that can make 15. Now if you experiment with that for a moment, you'll realise that the central digit has to be 5. And the way you can prove that to yourself is that once you put a 5 in here, there would then need to be four different ways of making 10. And there are 1, 9, 2, 8, 3, 7 and 4, 6. So 5 has the unique property that it can be part of four different ways of making 15. And then you can go further than that by thinking about, because we can actually tell some things about the digits on the corners here, which equates to those four squares. Because each one of these we know has to be part of two individual sums. So let's think about, if there's a 5 in the middle, let's think about the number 9, for example. If this was a number 9, we know this would be a 1, because that has to be 15. How many other ways are there of making 9? Or making 15 using a 9 if we can't use a 1 and a 5? Well, there's only one other way, and that's with 2 and 4. So actually 9 does belong at the centre of an edge, because if we put it in the corner there would need to be 3 ways of making 9, and that's not possible. And if you experiment around with this, you'll find that actually what happens is that the even digits end up in the corners of the magic square, and the odd digits lie in the middle of the edges. And that is, I suspect, going to be extremely important in terms of trying to solve Ard's puzzle. So in fact, what we're able to do straight away is we can write a 5 in here, because it's the centre of the magic square. We can write a 5 in here, and we can use the parity constraint to say some things about the centre of edges. So those 4 squares have to be odd. These 4 squares have to be odd. So I'm going to colour odd squares in blue. Now I'm going to do that because if we know that these diagonals are also odd, then we've got a tremendous amount of information about the parity of the grid. We might be able to use that to solve the puzzle. So now if we know the corners of the magic square are even, let me make sure I actually highlight the right squares. Oh, goodness. Then we can have a stare at the grid and see if we can see any patterns. Well, yes, we can look at the central box. So the central box, of course, includes 5 cells that are on the diagonal. We know they all have to be odd. There are only 5 odd numbers between 1 and 9 inclusive, so the others must be even. And immediately we get a constraint look. Now in row 5 and column 5, we have 4 even cells. So the other squares must be odd. And I suspect this is going to be the key to solving the puzzle. Now, let's try and... So all I'm doing now is just scanning the grid in rows, columns and boxes and trying to find clusters of the same coloured square. And I'm actually failing to do that. No, okay, so Okay, so we need to think harder. I really don't want to label all of these squares like 1, 3, 5, 7, 9. That is going to be very difficult to sort of get your head round. So, actually that square can be a 2 or a 4, can't it? Because that can't be 6 or 8. So that square is reduced to a pair. And if we look at, I mean, there's only 4 given digits here, and even with the 5s don't really communicate with each other in any useful way. So I am wondering what we're meant to do here. I mean, if you look at this digit, this 6 does almost nothing for the solve, because it rules out a 6 from this corner of the magic square, but this could still be 2, 4 or 8. And that, I mean, there being no 6 here removes the possibility of a 4 here. But again, that is a very minimalist restriction on this magic square. The 3 is the same. The 3 only actually rules out a square from one centre of an edge here. I mean, this 1 is a bit better. The 1 at least rules out 2 squares, or 2 centres of a vertex. So the one on this magic square has got to be in one of those 2 cells. I'm just going to use this notation for a minute to try and spot things. I wouldn't normally put notation outside of the same 3x3 box. The 8 as well, actually this is, so we're going to have to look up here, I'm sure, because the 1 and the 8 are much more powerful than the 6 and the 3 in terms of how they operate on this square. So the 8, you can see it gets rid of an 8 from this square and this square. So in this magic square, the 8 is forced into one of those 2 positions. Ah, now that's it. That is the trick. Okay, can you spot it? If you can't, this is an opportunity to pause the video, because once you know what we have pencil marked here, it's not too difficult, I think, to see the issue. And it's a beautiful idea. I mean, you don't expect anything less from art, but the trick, I think, is to notice that these 1s must always be opposite 9s on the magic square, because if we have a 1 here, it goes through the 5, it'll hit a 9 there. This 1 will go through the 5 and hit a 9 here. And why is that a problem? Well, these 9s pinch this 8. So if this is an 8, it doesn't matter which of these is a 9s, which of them is a 9, one of them will be a 9. And why is that a problem? Well, 8 plus 9 is more than 15, so that is absolutely impossible. There can never be an 8 here, because we know there's a 9 in one of those 2 squares. Now there you go. So this square is an 8, and it must be opposite a 2 to make 15. And then we can just continue the logic, can't we? Once we know the position of the 8, it can never be next to a 9, so that cannot be a 9. Ergo, that cannot be a 1. So this is a 1, and this is a 9. And now we're going to finish the magic square, because we've got so many bits of it already given. That's going to be 6, that's got to be 4, that's got to be 3, and that's got to be 7. That is progress. Now this 4, look, that sees a 2 there. So now just let me stare at this for a moment, just to see if I can see anything else. This 4 is nice because it rules a 4 out from that cell. So the 4 must be in one of those 2 positions. And that's massive, because now this cell, which is even, can't be a 6, can't be a 2, can't be a 4. That's got to be an 8. And that's on the magic square. So 8, 5 has got to be 2. Now, what can we do from there? must be able to do some more with this magic square, I feel. We've got... Well, this square here can't be a 3. What am I missing? I'm not sure. Are all magic squares of this, of 1 to 9 size, perhaps they are all the same? Are they all reflections of each other or rotations of each other? So perhaps once you know this is 8, 5, 2, there always has to be a sort of 1, 3 pair in these positions. Anyway, let me try and do it properly. So 2. How many other ways are there of making? I need 13 into both of those cells. So these have to be 4, 9, and 6, 7 in some order. But the 9 can never be in the same set as the 8. So the 9 can never be here and here. So the 9s always go there and there. Yeah, I think these are going to be reflections or rotations of each other, aren't they? Maybe I'm wrong about that. So this, we now know the 4s must be in one of those positions. And look, this 4 up here, which we already looked at in the context of this box, I should have appreciated has an effect on that square. So this is a 4. Now that square's got to be 6. That fixes that one as a 1. That's a 9. That one must be 7. That one must be 3. Oh, and in fact, oh yeah, we've got identical magic squares in this grid. that's mad. Okay, so now the 8 must go here in the central box, because obviously it can't go in either of those 2 squares. Those 2 squares are a 4, 6 pair. 6, look. No, not quite. 7. Oh, 3. These 3s lock a 3 into one of those cells. There's a 3 in one of these 3 positions. Where does 3 go in this box in the centre? This 3 and this 3. Rule out those 2 squares. So there must be a 3 here. Places a 3 over on the left-hand side. Those 2 squares have got to be 5 and 7 in some order. Fours in this box. This 4 and the 4s there lock a 4 into one of those squares. So there's a 4 up here. Sorry about this. Let me just 6. Look, these 6s lock a 6 into one of those 2 squares. Oh, that's nice, because that gives me a resolution to my 6-4 pair in the middle. So that's a 6. That's a 4. Now there's a 4 down here. 5, 7. Oh, I tell you what, where does 5 go in row 4 of the grid? We've got a 5 here and a 5 here. So it can only go in this cell. That's the only option. Nice, because that gives us a 4-5 pair in this, in box 3 now. So that's a 4 and a 5. Ah, and of course the diagonal now. Lovely. So the diagonal disambiguates this. This can't be the 4. So we can place the 4 at the top, the 5 down there. 5 must be in one of these cells. 4 must be in one of those cells. Okay. So these 2 have got to be 1 and 4 in some order to complete the row. 6. Oh, where does 2 go in this box? This 2 and this 2, push it here. So that's been there for a while. That's a 2 therefore. 2 is forced into one of those two positions. Right, now this is why, or one of the reasons we use pencil marks, because look, I've got 2s and 6s now locked into the same 2 cells in this grid. So ask ourselves the question, can this be a 5? No, because if I put a 5 there, the implication of a 5 there is I have to put a 2 and a 6 in this cell. And there's no such thing in Sudoku as a Schrödinger cell, although we did christen a technique based around it. So this one can't be 5. It's a 5 here. This is a 2-6 pair. That 5 disambiguates the 5-7 in the middle. Now where does the 7 go in this box? Look, it's got to go here, which fixes the 4, which fixes the 1. These two squares have got to be 9 and 1. We can do that. Those two squares have got to be 7 and 8. Now let's look at this box now. That 7, 8 is interesting because we've also got 3's pencil marked, yet we know this cell has to be odd. So it can't be 3, it can't be 5, it can't be 7, it can't be 9, it must be 1. That places a 1 here by Sudoku. These two squares have got to be 3 and 6 to complete the box. 6. So 6 in one of those two cells. Now let's have a look along here. We've got 7 digits here, so we need 3 and 5 to complete the row. Now this 3 is important because that locks a 3 into one of those 3 cells in box 1. Now the important thing to note there is it's in the same column, it's in column 1 and 2 as the 3 is in this box, in box 4. So we can ask ourselves the question, where does the 3 go in column 5? Sorry, column 3, sorry. We know it can't go in those 6 squares, so it must be in one of these 3 squares, and our pencil marking tells us which one it is. Those squares there have got to be 4, 6 and 9. I'm just going to pencil mark that in. That one can't be 6. Oh, this one, look. We can, the 1 in fact tells us the order there. That's a 1. That must be 9 up there. Okay. I'm going to have a look at this column now. We need 3, 6 and 9 again. Look, that one is very nice because the 3 and a 9 in the row, that's going to be a 6. That disambiguates the 6 and the 2. Where does the 2 go in this box now? Well, it can't go in the odd square, so it's got to go in one of those 2 cells. In fact, there's a 2 there as well, so it's actually got to go right at the top. 2 gets pushed into one of these 2 cells in box 7. Those 2 squares are 7 and 8 in some order. The 7 down here tells us which. And I think we're starting to make reasonably decent progress here. We've got 3, 7 and 9 to place. We can do that. Actually, we can do all of that. Yes, 3, 6. That's got to be a 3, I think. 4 and 7 into those 2 squares. That one's got to be the 9. That's not 9. Okay, what can we do down here? So if we look down this column, we've got 2, 4 and 8 to place in these 3 squares. That one can't be 4, that one can't be 2. And in these 3 squares, therefore, we've got to have 5 and 9, and the 5 disambiguates it. 5, 9. 5 must be in one of those 2. 9 must be in one of these 2. Okay. So where should we look now? It's probably going to be... Should we check this column? 4, 6, 7 and 9? Yes, because that square is interesting. It sees a 6, 7 and a 9, so it must be a 4. That fixes the 4, 7 at the top, fixes a 4 here, and a 9, and a 6. That fixes a 6 there. This column needs a 9. That's going to have to go there. That 4 removes that as a possibility. So if we look at this row now, we still need to place 2, 5 and 8. No, actually that doesn't look like it's the key to finishing this off. Oh, it is. Of course it is. Sorry, I'm forgetting we've got a diagonal here that has to be odd. So there's no way that square can be a 2 or an 8. It's a 5. Goodness me. And that one's a 2 therefore. That's an 8. Oh, that's a 2 and that's a 4. Hope I haven't made a mistake there. 3, 5 must be resolved, and it is. That square ought to be an 8, which is important because that resolves the 8 and the 7. That gives us a 7 and a 1. Check, and we are done. Odd, yet again, absolute beauty in the form of a Sudoku. Guys, I hope you enjoyed it. Do let me know in the comments, and we'll be back later with another edition of Cracking the Cryptic. And of course, big thanks for the subscription numbers. It means a lot to us.